Hi, everybody. Thanks for coming to today's lecture. Today, we are talking about carbon capture and removal technologies. I'd like to thank all of you who have been watching the lectures so far that I've been posting on YouTube. If you've been enjoying them and want to learn more, please subscribe to my channel, and you can even set up notifications to see when I've posted a new lecture. So there's really three types of carbon capture or removal technologies that are in use currently. There's absorption, adsorption, and membrane separation. Now, what I'm going to talk about in this lecture is only going to be absorption and adsorption. Membrane separation doesn't really work that well for carbon capture. And the reason for that is that your incoming gas stream is usually at a pressure that's close to atmospheric, and membranes usually like to operate at much higher pressures than that. So it's not particularly efficient for carbon capture right now. Now, that doesn't mean that new technologies can't be developed in the future, but right now, absorption and adsorption are the two main ones that are used there. So let's talk about absorption first. So absorption is when a liquid solvent causes the CO2 to become dissolved, and then it's moved to a separate facility to exsolve that CO2 and produce a high purity CO2 waste stream. So this is a diagram of a very generic liquid solvent absorption system. So what happens here, this would be like something you would have attached to a power plant, for instance. So your flue gas comes in here, and let's imagine it's got 15% CO2. Then what it does is that flue gas reacts with a hot solvent, usually around 40 to 60 degrees Celsius. The majority of that CO2 will be dissolved in that solvent, and then the treated flue gas will come out. So you can see in this case, they're assuming we're capturing 90% of the incoming CO2. Okay, so the solvent containing CO2 comes out this pipe here, goes through this heat exchanger, and then goes into what's called the stripper column. And the stripper column heats up that solvent, usually to something between 100 and 140 degrees Celsius, and that causes the CO2 then to exsolve, and the waste stream that comes out of that is very high purity CO2. The solvent now does not contain any CO2, and so it goes back through the heat exchanger and then back to the absorption column. So it's a pretty simple system, and it's fairly efficient. Now, you have to pick the right solvent to get this process to work properly. So these are the qualities that we look for in a good solvent for absorption processes. So we want it to have a high working capacity, and this means that you can absorb more CO2. Okay, so that's obviously a good thing. We'd like it to have a higher heat of absorption, and this means that it's going to have a higher vapor pressure, and there will be more CO2 content and lower water content in the gas that leaves the strip. So basically, you have to remember that absorption releases heat, and so we'll be operating at a higher vapor pressure, and we'll be able to purify the CO2 more easily. We obviously want the solvent to react well with CO2. We want it to be able to capture that CO2. And we want good thermal stability. So it has to be able to operate at high temperature, and the higher the pressure we can operate at, the better, because then this will allow the solvent to carry more CO2. And lastly, we want to have a lower viscosity, because that makes it easier to pump. You have fewer frictional losses, and the pump efficiency is improved as well. So there are several different solvent types that are used in these types of systems. You can just use pure water if you're into that sort of thing, but you can improve on that. So you can also use aqueous solutions of either sodium hydroxide or potassium hydroxide. These are particularly efficient at low CO2 concentrations, and so I'll talk about these in a minute with respect to direct air capture. The problem with these is that they have a high heat of absorption. And so to get them to break down and release the CO2 again, you need to heat them up to a very high temperature. So that requires a lot of energy for that final separation. Aqueous amines are probably the most widely used solvents. Monoethanol amine, also known as MEA, that's their primary amine. This is, by and large, the one that's used the most out there in the industry. Tertiary amines can actually absorb more CO2, but they react very slowly. So you can speed this up with enzymes, but that's just another chemical you have to throw in there. And so that's why a lot of people are still using MEA. You can also use these things called ionic liquids. These are large molecules that carry a charge. They're either cationic or anionic. They're liquids at room temperature, and there's some interesting emerging research right now on their use as a CO2 solvent. So let's talk a little bit about how this actually works. I'd like to introduce you to Henry's law. Henry's law relates the pressure of a gas in the vapor phase to the concentration of that same gas as a dissolved phase in a liquid that is at equilibrium with this gas, okay? And so this law here states that if you multiply the mole fraction of CO2 in the vapor phase by the vapor phase pressure, it'll be equal to the mole fraction of CO2 in the liquid phase times this constant, which is called the Henry's constant. And you can think about this representing a linear relationship. So if I have a particular amount of CO2 in the vapor phase and a particular amount of CO2 in the liquid phase at equilibrium with the vapor phase, you should be able to draw a line that relates the two of them. And that line is going to have a slope of Henry's law divided by the pressure, okay? So that's really all that this is saying. It's a very simple way of representing vapor and liquids at equilibrium. Okay, so to understand how an absorption system works, now I'm going to introduce you to this McCabe-Thiele diagram. And this tells you where your system is operating with respect to the equilibrium line. So remember again, this blue line, that's our Henry's law equilibrium. So along this line, the vapor phase, the pressure and concentration of CO2 in the vapor phase is going to be at equilibrium with the concentration of CO2 in the solvent, okay? Now, we are going to start above that line. So the incoming flue gas is going to be at some concentration of CO2 and some pressure. And we want to remove most or all of that CO2 from the vapor phase and get it to dissolve in the water phase. So we need to start above that equilibrium line to drive that reaction to absorb that CO2 into the solvent. And typically this is done in a series of stages within the absorption system. So we can draw what these stages do just as a series of vertical and horizontal lines. So in the first absorber stage, we're starting at the incoming flue gas, and we will absorb the amount of CO2 out of that gas stream to get us down to the equilibrium line. Now, we can't absorb any more CO2, right? Because that's going to violate Henry's law. We'll be out of equilibrium there, okay? So we come down here to this first absorber stage. Then we're going to be at the same composition of CO2 in the vapor phase, but we can pass this then to another absorber stage where, again, we're going to be operating above equilibrium. And so then we'll do the same thing again. Second absorber stage, we'll take up some more of the CO2 down to the equilibrium line, and then we'll pass it to another absorber stage. And we'll keep working on this process and so on and so forth. So the deal with this, though, is that you can't do this, ad infinitum. You cannot remove 100% of the CO2. And the reason for this is what we talked about in the previous lecture, which is that it takes more and more and more energy to separate the CO2 as the concentration of CO2 in the gas feed goes down. So, you want to do a cost-benefit analysis to say, okay, how much of the CO2 can we reasonably capture before it's not going to be worth it to do it anymore? Okay. So that's the trade-off you're looking at. But this is the basic way that these absorption systems work. Now, you've probably been hearing a lot recently about direct air capture. This is a thing that's been in the news a lot because rather than having to position yourself at a point source of CO2, like a coal-fired power plant, the idea is that we can build a lot of these direct air capture systems and then just put them out all over the country and all over the world and just keep, pumping CO2 out of the atmosphere. It's somewhat of an inefficient process, but there's a lot of improvements that are being made on that. So these direct air capture systems, they use aqueous hydroxides, like I mentioned earlier, because they work very well at a low CO2 concentration. So, we're not talking about like 15% CO2 coming in. Obviously, we're down in the hundreds of parts per million range here. So it's considerably lower. This is what these systems look like. This is a small one here. This is the Climeworks facility over in Switzerland. And each one of these fans sucks in air and passes it through pipes to the absorption unit, which does its thing, and then the waste stream is depleted in CO2. So the way it works is the ambient air comes into the air contactor. That's each one of these little things here. That takes electricity, obviously. So, if you're worried about carbon footprint, you could use, solar or wind or something to generate that electricity. And then the CO2 in that air will react with either sodium hydroxide or potassium hydroxide, and that will produce one of these minerals down here. So those, the aqueous stream of those comes through here, goes through the air contactor, and then we get those mineralized forms there, which are still aqueous. And then it goes through a causticizer here, which then reacts these minerals with calcium to produce calcium carbonate. Okay, so then the calcium carbonate comes through here, and to get the CO2 off of this, you have to do a process called calcining. Okay, now calcining has to be done at a very high temperature to liberate that CO2. We're talking about 900 degrees Celsius. Okay, so that's really hot. It's considerably hotter than a stripper unit works in a typical MEA absorption system like what you'd have on a power plant. So that requires some type of tremendous amount of fuel and thermal energy input. So you're looking at maybe combusting something. Okay, there's additional CO2 that you're producing. So this is still a bit of a weak link that needs to be overcome. But then the result of that calcining, then say you have gaseous CO2, which then can be compressed and have something done with it, which we'll talk about in the next lecture. And then we produce calcium oxide, which goes through a Slaker unit, which combines that with water to make hydrous calcium hydroxide. So that's how the whole process works. As I mentioned, there's a couple of places where we need power input. We need electricity to run the air contactors, and then we need some kind of a heat generation source for the calcining. So, but it's a pretty simple system, and it can be scaled up pretty easily. Okay, so that's absorption. Now, let's talk about adsorption. And it's, it's such a shame that those two words are so similar to each other. Okay, so what's the difference between absorption and adsorption? Okay, so if you know your Latin, you know that the prefix ab means from, and then ad means to. All right, so we can think about that in terms of what the actual processes are. So in absorption, the gaseous molecules will soak into the other phase. All right, so they'll be taken out of the gaseous phase and then into the liquid phase. And so that's where the ad comes from. Adsorption is a process where the gas molecules, rather than going into the liquid phase, they actually stick to the interface. So they stick to, that's where the ad comes from. So we're not like dissolving something. So you can think of, absorption in terms of a sponge, where it's actually sucking in the liquid, like a sponge. And whereas adsorption is the molecules are actually sticking to the surface. So that's the big difference. Now, there's two different types of adsorption. There's physisorption and chemisorption. So physisorption is a very simple process where the gas molecules will stick to a surface just due to attractive van der Waals forces. Okay, so this is just driven by, induced dipoles and London dispersion forces and all that good stuff. Chemisorption, on the other hand, is adsorption, where you're actually forming chemical bonds between the surface here and your molecules. So we can use both of these to capture CO2, so we'll talk about them each. Now, the physisorbents, that's a tricky word to say, that are commonly used include zeolites, activated carbon, and clays. Zeolites are a transition metal oxide, so it's usually silicon or aluminum, and it's arranged in a regular geometry that can be very carefully controlled. So here's a ball and stick diagram of one of these zeolites. So the red's going to be your oxygen, and then the tan, that's going to be your transition metal. This one, to me, looks like it's silicon. And then there are preferential sites in the structure here where CO2 will sorb, and it's based on free energy minima. And this diagram here, this is actually a molecular dynamics simulation model from Lin et al., where they've actually color-coded here kind of these potential wells where you can get the CO2 molecules to stick. So there's a lot of great material science design that can be done on these zeolites to really enhance their CO2 physisorption capacity. Activated carbon is a really great physisorbent. This is used a lot in like water purification and that sort of thing. And the reason that it's so good is that it is a chemically heterogeneous surface that has a lot of different functional groups and a lot of different binding sites where things can stick to it. So this activated carbon, it consists of a regular carbon structure here. So you can see these hexagonal rings here. And then there's all kinds of different functional groups sticking off the ends, carboxyls and phenols, ketones, and all kinds of other good stuff. And those different sites will, tend to adsorb different chemical species preferentially. So this, works really well. It typically has a very high surface area, and so you can stick a lot of CO2 on there. Clays can also be used for this. So similarly, clays have a very large surface area, and they have a surface chemistry that allows CO2 to be adsorbed in surface complexes by surface complexation. There are a bunch of different sites where CO2 can go. There's these hexagonal voids. It can go in here in some of the interlayer spaces. If the clay is hydrated, this helps out a lot with its sorption capacity. Now, there are also various types of chemisorbents. Okay, so we've already seen a couple of these in our talk about absorption. And so in this case, we're not dealing with aqueous phase here. We're actually dealing with a solid substrate that does the chemisorption. So again, we have our basic metal oxides, and I use basic here in the pH sense, not the complexity sense. And they obviously will react with the CO2 to form various carbonate minerals. So that's pretty straightforward. Amines are back again. We know that these react very well with CO2. These are for chemisorption. Typically what we do is we create what are called amines on supports. So we start off with some kind of a nanoporous material, some kind of a polymer or something like that. And then we impregnate that with our amines that we're actually using for the sorption. So there's, this is one particular application called a molecular basket sorbent, MBS, where the inner part of this nanoporous material is filled up with these amines that'll soak up the CO2. And then finally, there's an interesting group of materials called metal organic frameworks. These are organic ligands, so similar to small, short polymer chains that are coordinated with metal ions. And they form an open microporous structure. So you can think this diagram here, the black spots are going to be your metal ions, and then the white sticks will be your organic ligands. And so you can see there's a very open porous structure here, and you can use that to soak up various things, including CO2, through careful material design. Okay, so how are these things actually applied? So it's kind of a similar process to adsorption. So there's two types of reactors that can be used for adsorption processes. There's a fixed bed reactor, then a fluidized bed. So a fixed bed reactor is really simple to understand. The flue gas comes in, and then the CO2 adsorbs on whatever is in there, and then the exhaust gas comes out, and hopefully it contains no CO2 or very little CO2. Okay, now the problem though is that there's going to be a maximum absorption capacity of the material that's in here, and so periodically you have to flush out the CO2. So you'll shut this thing down and then flow a purge gas through here in the opposite direction to push out the CO2 that's been adsorbed and can be captured. Okay, so it's a really simple process, but it does have to be shut down and purged periodically. So that's the main drawback of that. Now, the fluidized bed, on the other hand, it's more of a complicated system, but it does allow for continuous operation. So the way that this thing works is that the flue gas comes in at the bottom of this adsorption section here. And so the gas flows up, and then there's going to be these particles of your adsorbent, which are falling down through a series of trays here. And as they do that, they'll react with CO2, and eventually the gas that comes out of the top of the reactor will have little to no CO2 in it. And so then what happens is that those particles that contain the adsorbed CO2 will fall down here into what's called the desorption section, where they'll be heated up to cause the CO2 to come out, and then you'll collect the particles and then re-inject them at the top. They'll be carried up in this carrier gas to go up to the top. Okay, so it's a lot more complicated, but it does allow for a continuous flow. So there's pros and cons to both of these. So how can we describe the adsorption process mathematically? So there's a really simple way of doing this. So let's imagine we've got a solid adsorbent with some maximum number of adsorption sites. We'll call this N max. And here I'm going to mark them with X's here on the surface. Okay, so let's imagine then that we introduce our CO2 to this surface. What's going to happen is that a certain fraction of the total adsorption sites will experience adsorption. Not all of them, just a certain fraction. And so we're going to call that fraction theta, all right? And we'll assume that each one of these adsorbed molecules does not interact with any of the other adsorbed molecules. So it's purely a one-off, one-on, one-off type of process. Okay, now, when we think about kinetic theory, we have to understand that this, is going to be a thermodynamic equilibrium, but what's going to be happening is that we're going to have some molecules adsorbing to the surface and other molecules desorbing from the surface continually at equilibrium, okay? And so we'll say that the flux of molecules leaving the surface, so desorbing, is going to be proportional to the total number of molecules on the surface, okay? So we'll call that flux K desorption, and that's just simply going to be a constant of proportionality. We'll call it C desorption times the number of sites that have sorbed gas molecules, right? So that's going to be theta times maximum number of sites. Okay, in the other direction, the flux of molecules adsorbing on this surface is going to be proportional to the number of molecules here in the gas phase. Okay, again, this is basic kind of diffusive kinetic theory. And the number of unoccupied sorption sites. Okay, so we'll say that the rate adsorbing, K adsorption, is going to be a constant, again, times 1 minus theta, so that's the times N max, that's the number of available sites. And then we'll use pressure to represent the number of gas molecules that are still in the gaseous phase. So again, this is invoking Henry's law, which we just saw. Okay, so at equilibrium, the two fluxes must be equal. So we'll relate the desorptive flux to the adsorptive flux. And if we do a little bit of algebraic manipulation, we can actually solve for theta. So this is going to tell us what fraction of the surface sorption sites are going to be occupied at a particular pressure. So here's my, showing my work here, so I get full credit. And so we end up with this expression here. So we have theta is equal to this expression over here. And we can simplify this a little bit and get rid of one of these constants. So if we multiply the top and the bottom by 1 over C desorption, and then define a new constant as the ratio of those two constants for adsorption and desorption, we get this expression here. So theta is a function of pressure and then some constant. This equation is called the Langmuir isotherm, and it describes the fraction of surface sites that will be occupied at a particular pressure on a sorbent. So one thing that the Langmuir isotherm predicts is that as you go to very high pressure, you'll approach 100% site occupancy. And the other assumption is that adsorption and desorption are completely reversible. There's no penalty for either. Now, we call this an isotherm because this describes adsorption at a constant temperature as a function of pressure. But there are ways that we can describe how adsorption is going to change as a function of temperature. So let's go back to our Langmuir isotherm. So let's talk about operating at relatively low pressure. So if the product of B and P is much less than 1, this term in the denominator is going to be approximately 1. So we can say that theta is approximately equal to the product of B and P. Okay. And now we can recast this in terms of the absolute number of adsorbed molecules. Okay, so theta is just number of adsorbed molecules at a particular pressure divided by the maximum. And so that's equal to BP. And so we just can distribute that and come up with this expression here. And as it turns out, now we're back here at our Henry's law coefficient. Okay, so number of adsorbed molecules is simply Henry's constant times the pressure. Now this is nice because then we can use the Van 't Hoff equation because that describes how the Henry's coefficient changes with temperature. That's this equation down here. So this is cast in terms of the heat of adsorption. Okay, so this tells you what the change in Henry's law constant is going to be with temperature. R, of course, is the universal gas constant. So we can go ahead and integrate this. So here's the Van 't Hoff equation. We can set up this integral here. So the change in the natural log of K is going to be given by this integral here between two temperatures. And if we work through this integral, we arrive at this expression here. So we see that if we're talking about going from a lower temperature to a higher temperature, so T2 is greater than T1, that means that this term in parentheses is always going to be positive, okay? And because adsorption is an exothermic process that releases heat, delta H is actually negative. And so what this means is that this whole term here is going to be negative when you're going up in temperature. And so what this means is that the Henry's law constant will decrease with increasing temperature, and it means that less and less can be adsorbed at higher temperatures. So you want to try to limit the temperature at which you're working. Okay, so one way of working with fixed bed adsorbers is to do a process that's called temperature and pressure swing. Okay, so we start off with a temperature swing. Okay, so when we're adsorbing here, so here's our fixed bed column, and then what we want to do is we want to sweep out the CO2. And so what we do is we will sweep with a cooled gas. Okay. And so what this allows us to do is we can inject at a higher pressure than what we were initially working at. So it pushes out the CO2, but because we're working with a cooled gas, it actually, due to that temperature effect we just talked about, it causes the CO2 to desorb. Okay. So this is a plot of the pressure of the CO2 versus the sorbed capacity. And so you can see that if we are working at a low pressure during the adsorption phase, but at a higher temperature, if we reduce the temperature, that means that we'll be able to work at a higher pressure. Okay, so that's our temperature swing. We can also use what's called a pressure swing. And so the pressure swing is just when we use a sweep gas that's injected at a lower pressure. It doesn't have to be cooled. And so in this case, we just work our way, we're at the same temperature, we just work our way down in terms of pressure. And so that's going to cause the CO2 to come off. So these are the two different ways that you can work your sweep, your purge gas in a fixed bed adsorption. Okay, so I hope you've enjoyed hearing about carbon capture and removal technologies. Next, in our next lecture, we'll discuss what to do once you've captured that CO2. So thanks for listening, and I hope to see you on the next one.